Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is Chapter 3, Section 7, so 3.7, which is related rates. Right? And, alright, so consider the following scenario. Let's say that I took a pebble and I threw it into a pond, right? So, pebble in a pond. And, well, what happens? When you first throw it into the pond, it falls right into the center, right? And then after a little bit, you end up with like a ripple, right? Let's say that's after some time. And then after that, you end up with a second ripple after some other time. And then after that, you end up with another ripple, right? And so on and so forth. Now, the idea here is, well, that there's a lot of stuff changing throughout time, right? This is a time 0, it's not the original time. And what are all the things that are changing, right? So what is changing? Well, we have the radius changing, right, throughout this entire time. We have the radius entirely changing in all those pieces. Now, I mean, along with the radius, we can also say the diameter, right? But what else is changing? We could also say that the circumference is changing, like, right, all these circles, they all have different circumferences. Circumference. And what else? Well, the area is also changing, right? So all of these are changing, all right? Um, but in here, the rate at which every single one of these things are changing, right? They're all related, all right? And they're all related to the same event. And the event was dropping a pebble into the pond, right? And that created all those ripples. Um, so in here, the way these are all changing, we can consider them functions of time, all right? So we can say that these are changing with respect to time. So we can consider them functions of time. All right. So, all right. So now let's see how this idea was going to work here with calculus. All right, because what we're trying to do here in calculus is we're trying to use we're trying to figure out how all of these are changing and how to measure the rates of all those changes. All right. So let's go ahead and start an example here. So let's say, let me set it up. The variables x and y are both differentiable functions of t, all right, and are related by the equation y equals 2x squared plus 1, all right. The question here is find dy dt when x equals -1, given that dx dt equals 2 when x equals -1. All right. So in here, well, we have each of these variables y and x, where they're both functions of time. All right, or excuse me, functions of t. In general, we like to use the variable t for time, right? So what do we have here? Well, we're looking for dy dt, right? So we're looking for dy dt. And if you recall, the chain rule was that dy dt is dy dx times dx dt, all right? And I mean, these are not technically fractions, but if they were fractions, it would make sense, right? Because these just cancel out and you end up with dy dt, but they're not technically fractions. And it's just notation. But now, in here, well, what does that mean? That means we gotta figure out what dy dx is and multiply it by dx dt. Okay, so then dy dx is, well, the derivative of y with respect to x, which is just 4x. So what we get now here is that dy dx is, well, 4x times dx dt, whatever that is, right? We don't actually know what it is overall. We knew what it is when we plug in x equals 1, gives me x equals -1, right? So this was dy dt. So that tells me now that dy dt when x equals -1 is going to be, well, x is -1, so I have 4 times -1, and dx dt is 2 when x equals -1. So what we really get here is -8. All right. So we just found that dy dt is -8 when x equals -1. All right. Now, in general, the way that I did it here, while it is everything about this is correct, it's not really how I would want you guys to do this. So let me show you how I would want you to do this without necessarily using this notation the way that it's there. So what we can do here is we can think of these two variables. Well, they're variables of t, right? So they're functions of t, excuse me. So in here, when I go and find dy dt, so I'm taking the derivative with respect to t. Well, I know that x is a function of t, so what we can essentially do here is we can treat this as implicit differentiation. So I take the derivative, so I end up with 4x times dx dt. So essentially, whenever I take the derivative of a function of t, I multiply by dx dt. All right, I mean, from here on, it becomes the same exact thing, right? Because that's what I have here. So we just will continue there. But again, the idea here is that since y and x are each functions of t, I can take the derivative with respect to t and use implicit differentiation. So let's do a similar or another example. So let's say the radius of a circle is increasing at a rate of 4 centimeters per minute. Find the rate of change of the area when r is equal to 8 centimeters. Also, find the rate of change of the circumference when r is also equal to 8. All right, so we're going to do both of those, and I'm going to call this question 1 and question 2 using Roman numerals. Let's rewrite that. Okay, so in question 1, it says find the rate of change of the area when r is equal to 8. So let's see what to do. We're working with area, right? So we're working with area. So I'm going to start with the formula for the area of a circle, right? Because we're working with a circle, the radius of a circle. So pi r squared, all right? Now, what's going on with the circle? Well, we see that the radius is increasing, right? The radius is increasing at some rate. So as far as the visual goes, well, what's really happening here? Well, what's happening here is essentially that ripple effect that I mentioned in the first, at the beginning, right? Where we essentially have all these ripples happening. Oh, that's beautiful. All right. Right, so that's the idea there. And this is happening throughout time, right? It's getting bigger and bigger. So in here, well, because the radius is changing with respect to time, the area is also changing with respect to time. So what does that mean? In here, both A and R are functions of time. So when I take the derivative using implicit differentiation with respect to t, what I get is, well, dA dt. I should take off this thing. Okay, so I get the dA dt is going to be, well, 2 pi r, but then because implicit differentiation, I'm going to say times dr dt, right? 2 pi r dr dt. And at that point, well, what I can say here is, well, I get 2 pi times. What radius do we care about? 8. So times 8. What's dr dt? Dr dt, well, they tell us the radius is changing at a rate of 4 centimeters per second. So in there, this tells us, so the fact that it says rate of 4 centimeters per minute, I think I said second earlier. I meant minute. So in here, what that really tells us, this information, increasing rate of that, is that, well, dr dt is 4, right? So in here, this dr dt, we're going to say, well, that's 4. So what do I get here? Well, 2 times 4 is 8, times 8 is 64. So here I end up with 64 pi, right? So that's dA dt. Now let's figure out units here. This is the change of area, right? The change of area with respect to time. And in here, the area, well, what are the units? Centimeters. So we're going to get centimeters squared per minute, right? That's the change of the area with respect to time. All right. So now let's do the second part. Find the rate of change when the circumference is equal to 8. Excuse me, find the rate of change of the circumference when r is equal to 8. Okay. So we're going to start in a very similar way. But now we're going to start with circumference. And circumference is equal to 2 pi r. So if I want the rate of change of circumference with respect to time, well, let's take the derivative of this. Remember, 2 pi is a constant. So I end up with just 2 pi, but by implicit differentiation, times dr dt. At that point, well, I know what dr dt was. Dr dt was 4. So I get 2 pi times 4, giving me 8 pi. And now circumference. What's the units for circumference? Well, circumference is just the distance, right? It's just the distance around something. So it's just going to be centimeters. And then with respect to time, so centimeters per minute. All right. So there you go. And that's the first example. Next example. Let's get up a notch a little bit. So that was B. C. All right. So let's consider the following scenario. A ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. All right, we're going to ask a few questions about this one. So the first question, and we'll tackle them one at a time. The first question here is, how fast is the top of the ladder, top of the ladder, moving down the wall. When its base is 7 feet from the wall. All right. So that's the very first question. So in here, let's get a visual to what's going on here. We've got a house, right? So here's my awesomely drawn house. And this house has a ladder leaning on its wall, right? So let's say that we have this ladder, and I'll do the ladder in blue. There's my ladder. All right. Now, this ladder is being pulled away from the wall at a rate of 2 feet per second. So that tells me here, well, let's name some of these sides. In general, I like to name horizontal things x and vertical stuff y. All right. So in here, this distance is x. So we're naming that x, the distance from between the wall and the base. And this one over here is going to be y. All right. And now, so in here, we were told that the base is being pulled away at a rate of 2 feet per second. Well, that really tells me that the change of x with respect to t, right, this one is being pulled away, is 2 feet per second, right? Because this is being dragged that way at 2 feet per second. The question is, well, as that ladder gets pulled away, right? So for example, at one point, it's going to look like this, right? It's going to be all the way down here. So as the ladder pulls away, how fast is this going down? So essentially here the question is, what is dy dt? All right, that's the actual question. Okay, so in here, well, let's think about this a little bit. We need to figure out some sort of way to relate these two variables, x and y, within this triangle so that we can use this information. Well, let's see. By the way, I missed this piece right here. The ladder is 25 feet long, so I'll go ahead and write that here before we continue. This is 25 feet long. All right, so as I was saying, we need some way to relate all these sides, right? And we've got a right triangle in there. One thing that you should think about anytime you think about a right triangle is the Pythagorean theorem. So in here, the very first thing we're going to say is, well, the way we're going to relate these sides is using the Pythagorean theorem, which in this case would be x squared plus y squared. Hold on, let me write that in white. X squared plus y squared is equal to 25 squared, right? A squared plus b squared equals c squared. So that's the Pythagorean theorem for this triangle. All right, so now that I've got that, well, I'm going to take the derivative of both sides here. All right, let me just shift this. I'm going to take the derivative of both sides, and I'm going to use implicit differentiation with respect to t, right? Because x is changing with respect to time, y is changing with respect to time. This ladder, this length, is not changing with respect to time, right? The ladder stays 25 feet long throughout the entire ordeal, right? It's not getting smaller or bigger. The position of it's changing, this height's changing, this distance is changing, but the ladder itself, it's not. So that's why this right here is going to be a constant. So let's go ahead and take the derivatives. So the derivative of x squared with respect to time is 2x dx dt. The derivative of y squared with respect to time, 2y dy dt. The derivative of a constant with respect to with respect to time is 0, right? Now, at that point, well, let's see what else we need to know. It says, how fast is the ladder moving down the wall when its base is 7 feet from the wall, right? So let's see. We know the value of x, right? The value of x is 7, right? At least at the time that we care about. At the specific time that we care about, the value of x is 7. And this side over here is 25. So from the Pythagorean theorem, we can figure out what y would be, right? So using the Pythagorean theorem, I've got 7 squared plus y squared is equal to 25 squared, right? So this tells me really that y is equal to technically plus or minus, but I'm going to be using just the positive version because we're dealing with distances here. So the square root of 625 minus 49, right? And 625 minus 49 square rooted actually ends up being 24, all right? This is a Pythagorean triple, 7, 24, 25, all right? It's not a common one. It's not as common as a 3, 4, 5, right? Or the 5, 12, 13. But it's still a pretty good one too. So 7, 24, 25. Now in here, now I've got all the values that I need. So I needed x. So now this tells me that I have 2 times x was 7, dx dt was 2. Y, well, y was 24, we just figured out. dy dt is what we're looking for, right? So at this point, solving for dy dt, well, I end up with dy dt is equal to, bring this to the other side, the negative of 2 times 7 times 2 divided by 2 times 24, right? Move this to the other side, divide. These two reduce, this 2 and that reduces, so I end up here with negative 7/12, all right? And what are the units? Well, the units where we were using feet and minute and seconds, right? So we were using feet and seconds. So in here, this would be negative 7/12 feet per second, all right? Now notice that this should make sense as to why it's negative, right? It's negative because this is falling. This distance is getting smaller. So the rate of change should be negative to make it go smaller. Whereas over here, where this distance was getting bigger, the rate of change was positive, right? So a positive rate of change means that it is increasing. A negative rate of change means that it is decreasing. So it makes sense that our answer is negative. All right, so that's the first question. Question 2. Consider the triangle formed by the side of the house, the ladder, and the ground. Right? Find the rate at which the area of the triangle is changing when the ladder is 7 feet from the wall. All right? So rather than redraw the visual, I'm gonna go ahead and copy this. Oh, that's not what I meant to do. All right. And recall that we were given the dr dx dt, the rate at which this is changing. We were given that was 2, right? It was 2 feet per second. Okay. So, all right. So let's again in this visual, this ladder is falling. So at some point it might look like this, right? But the question is, well, in there now I've got a different triangle, right? We're talking about this triangle on the inside here. This triangle, well, at some point it's gonna look more like that, right? And at some other point it might look more like that, right? Because it's just being dragged. Oh, the last triangle is horrible. All right, I'll leave it as that. So the idea here is, well, as this is falling, this area here, how is it changing? So what we want is dA dt, right? And the next thing we need to figure out is, well, how do we relate these sides with the area? Well, we know what the area of a triangle is. The area of a triangle is its base times its height divided by 2, or times 1/2. 1/2 base times height. All right, I'll go back to writing in white though. All right, so in here we want the rate of change of this, and remember we're thinking of x and y. We're thinking of each of them as functions of time, right? So in here, when I go ahead and take my derivative, so dA dt, well, in here I've got the product of two functions of time, so I need to do the product rule, and the product rule says the derivative of the first, so 1/2, but because I'm using implicit differentiation with respect to t, so it's 1/2 dx dt times the second plus the derivative of the second. Well, the derivative of y is just 1, but we're doing it with respect to t, so I end up with dy dt times the first, 1/2 x. All right, now let's see. We've got a bunch of this information already, right? Even this one, dy dt. If you recall from the last example, or the last problem, that's exactly what we found. Dy dt was negative 7/12. So it was negative 7/12 when x was equal to 7, right? Which is good because in here, that's exactly what we've got again. So we already have from the previous part that dy dt was negative 7/12. So now to figure out dA dt here, well, plug in the stuff that we know. So I have 1/2 times dx dt. Dx dt was 2 times y. What was y? Y we said was 25, right? So maybe I'll write it here. Y equals 20, not 25, 24. 24. So there it is, 24. Plus dy dt, which we just remembered it was negative 7/12, times 1/2 times x. X at this point is 7. So what do I end up with here? Well, these twos cancel out. Here I've got 24 plus negative is going to be negative. 7 times 7 is 49. So I have 49 over 48 there. All right. And at that point, well, what does that give us? Wait, hold on. What? I don't know where I got 48 from. 12 times 2 is 24. Okay, way better. All right, so now the next thing that we need here is a common denominator, right? And clearly the common denominator is 24. So here on the numerator, I'm going to have 24 squared, which is 576. So 576 minus 49. And 576 minus 49 is 527. So I end up with 527 over 24. And the units here are feet squared, right? Because of the change, the rate of change of an area. So feet squared, or per minute. All right. Now, if you really want to figure out what that is, in terms of decimals, well, it's about 21.96. All right, so basically 22. But I don't like decimals. I'm gonna leave it in terms of that fraction. All right. So next example, next piece. So next question, and we're still gonna be working with the same scenario, right? But we're gonna be looking for something else now. So question 3. Here I'm gonna say find the rate of change um, of the angle between the ladder of the wall, excuse me, the ladder and the wall, all right, and the wall of the house when the base of the ladder is 7 feet from the wall. All right, find the rate of change of the angle between the ladder and the wall of the house when the base of the ladder is 7 feet from the wall. Okay, so let's go back to this visual. All right, and recall this is falling, right? This is going away. So in here, we're asking about this angle right here. All right, perhaps I should have done that in a different color. We're asking about this angle right here, that theta, right? Because we know that as this changes, as this falls, it's going to be over here, right? Something like that. And in there, I'm going to have a different theta to worry about, right? The angle's going to change. These are not the same angles. So the question is, how fast is that angle changing, right? So, well, what are we going to do here? Well, let's think about this. We need to figure out a way to relate this angle and these two sides. All right. Well, with respect to this angle, this side is the adjacent side. This side is the opposite side. Adjacent and opposite. So what we can do is we can use trig to relate these things. All right. So we're going to work here. Here we're going to say, well, what's a way to relate the opposite and the adjacent side? Tangent. So I'm going to say that tan theta is equal to the opposite over adjacent. We also could have used cotangent theta, right? That would have been adjacent over opposite, but tangent theta is way more common. So, all right. So what do we do now? Well, I need to figure out the derivative here with respect to t, right? Because what we want is d theta dt. All right. All right. So let's see. In here, I'm actually going to shift this down here. But the other thing that I'm going to say here is what's given. At this point, we're given that x was 7. We said y was 24. dx dt was 2. And dy dt was negative 7/12. Okay. I just wanted to write down all the information that we found already from prior parts. We also found the area, but the rate of change of the area, but that's not relevant for this problem. All of these will be relevant. All right, so let's go ahead and take the derivative here of tangent theta. The derivative of tangent is secant squared. So I have secant squared theta, but we're taking the derivative with respect to t. So times d theta dt. All right, x over y. We need to do the quotient here. The derivative of the top, well, with respect to time, it's just dx dt. Times the bottom, y. Minus the derivative of the bottom, dy dt. Times the top, x. All over the bottom, squared. So moving this secant squared to the other side, what that really tells me is that d theta dt is, well, dividing by secant is the same as multiplying by cosine, right? Because dividing is by multiplying by the reciprocal. So I'm going to write this now as cosine squared theta times, well, this entire thing over here. So I'm just going to copy and paste that. All right, so that's what we end up with there. Now let's go ahead and finish solving this, right? So cosine theta times all of that. All right, well, cosine theta. Well, I have cosine squared theta, but I need cosine theta. Cosine from the Pythagorean theorem is adjacent over hypotenuse. At this specific point, when x is 7, y is 24, right? So what I can say here is that cosine was the adjacent, 24, over the hypotenuse, 25 squared, all right? And what else do we know? Dx dt. Dx dt was 2. Y, it was 24 minus dy dt times x. All of this over y squared. So all of it over 24 squared. All right. So at that point, let's see what we actually have here. I'm gonna write this as 24 squared over 25 squared. Here I've got 24 squared, right? The reason I'm rewriting it like this is so that I can cancel out those 24 squares and not have to worry about their value. All right, on the numerator here, well, I have 2 times 24, that's 48, minus the negative becomes plus. 7 times 7 is 49, so 49 twelfths. All right, now, what do I already have so far? Well, this 25 squared, I'll stop right there, 1 over 25 squared. And this other stuff, well, common denominator is 12. The second fraction is clearly just 49, right? The second numerator. But the first numerator, 48 times 12, that is 576. And then 576 plus 49 is 625, right? So what we end up with here is 1 over, well, 25 squared, 625. Numerator, 625. And then all of this over 12. So at that point, these cancel out, so I end up with 1/12. All right. Now, in here, what are the units? All right. Well, in general, anytime we're working with angles in calculus, the units are in radians. All right. So they're in radians. So in here, there's going to be radians per minute, and that's d theta dt. All right. And it should make sense that it's a positive angle, right? Excuse me, that it's a positive rate of change, right? Because this angle, as this comes down here, it gets bigger, right? This is a bigger angle than this. So it should make sense that it is a positive rate of change. Now, in here, let's recap this problem for a second. We had just one very easy scenario, the very simple scenario, right? The simple scenario being that this ladder is sliding down the wall. But look at all the things that we found, right? And in this first part, in part 1, we were able to figure out, well, just knowing how this one is being dragged away, we were able to figure out how fast this is falling down. In the second part, well, we were able to figure out how the area is changing. I guess I could have also asked about how the perimeter is changing, right, overall, but we didn't. And then here I asked about the angle. Now these are just some possible scenarios that you can do, but these were all just given the Pythagorean theorem. So let's do another one. Another problem here. Let's say So this is example D. Let's say that I had an airplane that was supposed to say airplane. An airplane is flying at an altitude of 6 miles and passes directly over a radar antenna. All right. When the plane is 10 miles away from the antenna, the radar detects, not defects, detects that the distance s is changing at a rate of 240 miles per hour. The question here is, what is the speed of the plane? All right. So an airplane is flying at an altitude of 6 miles. All right, let's start getting the visual with that. An airplane is flying at an altitude of 6 miles. Okay. And it passes directly over a radar antenna. So let's say here that on the ground I've got this cool antenna, right? That's my awesomely drawn radio antenna. Now in here, well, what do we have? We have that an airplane passed right over it, right? And so here's my airplane passing right over it. Awesomely drawn again. All right. This is flying at an altitude of 6 miles. So this height is 6 miles. And then it says when the plane is 10 miles away from the antenna, all right, well, the 10 miles away from the antenna. So that means that at some point this moved away, right? So let's say that this is flying this way, and we end up with, well, I can just copy and paste my awesomely drawn airplane. And look at that. Cool. So at some point, this plane is a distance s away from there, and it is exactly 10 miles away. So at this point, s is equal to 10, right? The question is, well, how fast is this going that way? How fast is that plane going? Now notice that in general, this distance s is not fixed, right? As the plane keeps flying away that way, this distance s is going to get bigger and bigger and bigger, right? Now let's think about this problem. I'm going to call this horizontal stuff, I'm going to call it x. This vertical stuff, I'm going to call it y. All right. And in general, that's how I like to name things. Now, this y, well, we're given the value of y. The value of y is 6, right? And it's a fixed value. In other words, we're saying that the height of the plane is not changing, so it's a fixed value. But the other ones are changing, right? So at least with respect to time. So let's figure out how to relate all these. All right. Well, just like before, we've got a right triangle, right? And the way to relate the sides of a right triangle is using the Pythagorean theorem. So I'm going to start with the Pythagorean theorem. X squared plus y squared is equal to s squared. right? Um, in here, well, what's actually changing? Well, x is changing, y is not changing. So what I can do there is I can just think of this as 6 squared. S is changing, so I'm going to leave the variable. All right. So in there, when I take the derivative, right, and I want to take the derivative because I'm looking for rates of change, right? So the derivative here, and when I do it with respect to time, I end up with 2x times dx dt plus 6 squared. That's just 36. That's a constant. Its derivative is 0. S squared is 2s ds dt. All right. And what is that we really want based off of this problem? All right. Well, what we really want here is we're looking for x. So we want, excuse me, we're not looking for x, we're looking for dx dt. So want dx dt. All right. So that's all for dx dt here. Well, this here is not there, so I usually have dx dt is equal to s over x times ds dt. All right, so let's see what those values are. At the time that we care about, s is 10. What would x be? Well, I know the y value. This is 6, and this is 10. X ends up being 8. All right, this is essentially a 3, 4, 5 triangle, right? But it's doubled, 6, 8, 10. So in here, x is 8. So what do I get here? So x is 8. S at the time that we cared about, it was 10. ds dt, ooh, let's see. In the problem, we were told that the distance s is changing at a rate of 240 miles per hour. So that is the rate of change of s with respect to time. So now, so that's 240. Now we can say, well, 8 goes into itself once, 8 goes into 240 30 times, 10 times 30, 300. So dx dt is 300 miles per hour. So essentially that tells us then that that's how fast the plane is moving, all right? The plane is moving at 300 miles per hour. All right, so that was another example of the using the Pythagorean theorem, right, in this kind of problem. But let's go over a different example now. All right, let's make it more complicated. So that was D. So E, a conical tank with vertex down is 10 feet across the top and 12 feet deep. Water is flowing into the tank at a rate of 10 cubic feet per minute. All right. Find the rate of change of the depth of the water when the water is 8 feet deep. Okay. So let's get a visual for this. It says a conical tank with vertex down. Okay. a conical tank with vertex down. So we're working with a cone. So can this draw a cone? Let's see. Look at that beautiful cone. Um, so in this cone, what do we know about this cone? Well, we have that it is 10 feet across the top. Okay, so this distance and so this distance is 10 feet, and it is 12 feet deep. So this distance is 12 feet. Okay, and well, what else do we know about this? Well, we know that this is being filled with water. So at some point, the water level is here, right? Uh, Let me redraw that. So at some point, the water level is here. At another point, it could be up here, right? Because it's being filled in, right? So we have different points of where this water depth is throughout time. All right, so what do we care about here? The water is flowing into the tank at a rate of 10 feet per minute. Rate 10 feet per minute, 10 cubic feet per minute. So what that tells us is that the volume of this water is changing, right? This is these units are in volume. So what we have here is that the volume of the water is 10 cubic feet per minute. Okay. Next question. Well, this is the next part. Let's see. What we want is the rate of change of the depth of water. So we want, let's see, if I call this the height, right? If I call this the height of the water, so what we want is dH dt. All right, cool. Now in here, there's a lot of stuff going on. All right, and let's break this up a little bit down because there's a lot of things that we need here. We need to, well, here we're given the volume, right? The rate of change of the volume. So that right away tells me that I should be working with a volume function of some sort that includes a height. Well, in here, the volume of this cone, of any cone, is 1/3 pi r squared times height, right? And in here, notice that all of these things are changing with respect to time. The volume is changing with respect to time. The radius is changing with respect to time, right? This being the radius. If I draw this line here, these would be the radiuses at those respective times, right? And the height is clearly changing with respect to time, right? So the question here is, well, how do we find just how fast the height's changing? But now here's the thing about this problem. The radius is changing with respect to time. I said that already. But what does that imply? That implies that a dr dt exists. So here, this tells us that dr dt exists. So what? Right? So what? Well, that's a problem. And why is that a problem? Because, well, at no point were we given how fast the radius is changing. All we know is that the height's change, like how fast that we're looking for, how fast the height's changing, but we don't know anything about how fast the radius is changing. We know how fast the volume's changing, but again, nothing about dr dt, which essentially means we're gonna have too many variables when I go to take this derivative. So what do we do? Well, in this specific example, what we need to make sure we do is we need to write that radius with respect to the height. So we need to rewrite it somehow to resemble the height. And here's where this kind of problem becomes tricky. All right, because what we're gonna do is we're gonna work with this idea here. And what is that idea that I just pointed out? I just pointed out some random stuff, right? So let's look at that. I want to work with the fact that we've got something there called similar triangles, right? And here we've got two similar triangles, this water triangle and the overall triangle of the cone. In here, well, this represents the height of the cone. This represents the radius of the cone, right? This over here represents the excuse me, that this was not the height of the cone. This was the height of the water, and this was the radius of the water. This over here is the radius of the cone overall, and this is the height of the cone overall. But now, the radius of the cone, we know what that is. How do we know what that is? Well, the reason I know that is because we know what the diameter is. Since the diameter is 10, the radius is 5. And the height stays, the overall height of the cone, it's also unfixed, it's 12, right? Let's make more space here. Oh, 12. All right. So now, how is that helpful? Well, what we can do here is we can make proportions using these triangles, right? So what do I mean? I can say that this little h over this big H, so little h over big H, would be the same thing as little r over big R. How do I know that? Well, because these are similar triangles, all right? They're essentially proportionally the same. Or, yeah, that's a good enough phrasing. Anyway, in here, what I'm looking for is that lowercase h, because I've got everything else here, right? That lowercase h is just h for now, that big H. Sorry, I said we're looking for that lowercase h. No, we want to put things in terms of that lowercase h. Sorry. So now, this big H is 12. This little r we don't know. This big R is 5. So what this tells me now is that r, because I want to solve r into terms of h, is 5/12 h, right? That term is in h. So now that we've got that, well, we can go ahead and work with this formula, right? Because I've got what r is, 5/12 h. So really this formula is 1/3 pi times 5/12 h, 5/12 h squared times h, which is, well, 5 squared is 25, so I end up with 25 pi over 12 squared is 144. I'm going to write this as 3 times 144, and then times h cubed. All right. So now what? Well, let's see. We're looking for, again, dv dt, right? Excuse me, dh dt. So let's go ahead and take the derivative of this. So in here, dv dt would be, well, bring the 3 down, so I have 3 times 25 pi times h squared over 3 times 144 times dh dt, right? Because I'm doing implicit differentiation with respect to time, right? Well, what do you see? These 3's cancel out, right? And I end up with just 25 pi. Well, I'm not going to write that, because what we need to do here is we need to solve for dh dt, right? The problem is to figure out what dh dt is. And if I figure out what dh dt is, well, dh dt is going to be, I'm going to write this as dv dt times the reciprocal of all this, right? So times 144 over 25 pi times h squared, all right? Because I'm moving it to the other side with the dv, right? Multiply by 144, divide by all of this. The next thing, well, we know what dv dt is, right? That was the rate of change of the volume, and that was the flow of water into this, and it is 10 cubic feet per minute. So in here, what we actually have is 10 times 144 over 25 pi times h. What was the height at this point? At this specific point, the height was, where did I write it? Ah, there it is. We were caring about this when the height was 8 feet deep. So h is 8. So here I have 8 squared, right? And let's see what does that give us. Well, I'm going to try reducing this as much as possible, but first I want to have that 8 being squared, which is 64. All right. 5 goes into 10 2 times, 5 goes into 25 5 times. 64. Well, 64 is divisible by a bunch of stuff, right? It is divisible by, let's start by 2. 64 divided by 2 is 32. 2 divided by 2 is 1. Okay, next thing. 32 and 144. Well, they're both actually divisible by, well, let's start again simple. Let's start with 2. So 16, 72. 8, 36. 4, 18, 9, 2. And there you go. That's as far as we can reduce that. So we had 1 times 9 on top, which is 9, and 5 times 2 on bottom, which is 10. Oh, sorry, I forgot the pi. So 9 over 10 pi. And in here, this was a height, right? And our units were feet. So this is feet per minute. And notice that it's a positive value, which makes sense, right? Because the height, as this is getting fuller, as this tank is getting fuller, the height is increasing. It is increasing. Okay. Now that is the end of 3.7. All right, it's all about related rates. Now there are a lot of scenarios for related rates, but essentially it comes down to, well, reading the word problem and coming up with a visual, right? Once you've got that visual, it's well, how do you relate the things that are changing? You got to come up with some sort of formula that relates all the things that are changing, all right? And then that's once you have that formula, you have to take the derivative with respect to time, all right? And you have to be careful that you actually have all the things that you're going to need, right? Because like in this example here, I needed to make sure to change the variable r into something else because we did not have how fast that radius was changing, right? If I had kept it there, if I had kept that r there, we would have needed to figure out that dr dt, and in here, since we didn't have that, we didn't want to do that. Okay. Now, after that, it becomes just pretty much just a whole bunch of plugging stuff in, right? The hard things with word problems are always the setups, right? Being able to figure out what the setups are, and it's all a matter of being able to read the problems correctly. Look for keywords like rate, right? Once I have rate, that's telling me I've got some sort of derivative, all right? Notice in all of these, they were all using the word rate in general, rate. We were looking for speed. Well, speed is the rate of change um, of position, right? It is velocity essentially. In this one, well, in the falling ladder, there it is, rate of change, right? So in general, that word rate of change is gonna, or that phrase rate of change is gonna come up a lot, and those are the words to look for when doing these kinds of word problems. All right. All right. So like I said, that was the end of 3.7.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.